pass these out. I've got copies of my slides, which might be useful to some. So you're going to hear several things I'm going to say are going to echo things that our first two speakers have said. My goal here is to sort of give a big picture view of information, sort of from the Big Bang to today, and provide a lot of examples along the way. I'll start with my punchline. There are many kinds of information. Natural processes can create vast amounts of some kinds of information. Natural processes can convert or copy some kinds of information into other kinds of information. And we can understand and at least partially model where the information comes each step of the way, from particles at the Big Bang to ecosystems of complex organisms. Some we understand more, some we understand a lot less. Focusing in on origin of life is probably the one we understand least of all. And so there's a lot more to be understood about every one of these steps. But I think looking at the whole big picture will give you some sense for why I'm reasonably optimistic about the possibilities of research into origin of life ultimately coming up with scientifically understandable scenarios when you sort of look at the whole big story. I may be wrong, but you'll see why I think I'm optimistic. So this is both a list of 9 different kinds of information and sort of an outline of the talk. And I'm going to start with information required to specify rules and initial conditions, and then something called combinatoric information. So here's what I mean by combinatoric possibilities. You can have a small number of basic pieces which combine into a vast number of possible ways. So the information required to specify the rules and initial conditions of the system is small, but the information required to specify all possible combinations is vast. So, chess, 64 squares, 32 pieces, 12 types of pieces, 10 to the 85 different ways you can arrange those chess pieces. So the combinatoric possibilities information is vastly larger than the information required to specify the rules of chess. Another one I'd love to talk about in my physics class. Just 3 particles, I try and get my students enthused about this, 3 particles, electrons, up and down quarks, arranged into 100 different atoms, combined into billions of different molecules, each with their unique properties, into a mind-bogglingly amount of substances in living cells. Every solid, liquid, and gas in this room and all the different molecules in your body are different combinations of those 3 particles in some sense. So that's what I mean by combinatoric possibilities. Now, and one more. 4 nucleobases can be arranged to 4 to the n different ways in a strand of n DNA. It's another familiar possibility. I'm going to try and provide multiple examples each step of the way. Now, what do I mean by paths through combinatoric phase space? What I mean is that there are laws, both deterministic laws and probabilistic laws, which specify the moves you're allowed to make from one kind of arrangement to the next kind of arrangement. And so what you're doing is you've got this vast combinatoric phase space, and then the rules say, well, you can move from this spot to this spot, either absolutely all the time, or with a certain probability of going this way, a certain probability going this way, a certain probability going that way. So, for example, starting from the standard opening position of chess, there's estimated to be about 10 to the 120 different possible games, and each game would be a pathway through the combinatoric space of possible chess positions. And the rules of chess would specify from this position you can go to these possible positions with various probabilities, either randomly chosen equally or by rules of, well, probabilistically chosen from better versus worse rules weighted probabilistically. Starting from a vat of chemicals, you can ask, given certain energy inputs and the initial conditions, how many new molecules will be produced over time. That's worked out through the combinatoric paths. Similarly, point mutations and transpositions and duplications and deletions and other mutations can move you from one point in genomic phase space to other points in genomic phase space with various probabilities. So this is what I mean by paths through combinatoric space. All right, now the next one, contingent history of a system. Another kind of information. Each time a contingent event happens, means you're selecting one path through combinatoric phase space versus another path through combinatoric phase space, the contingent history information increases. And this is the process that converts sort of the potential information in the combinatoric phase space into really real information required to describe really real chess games, real objects, real environments, real computer programs, real genomes. So this is how we get that vast combinatoric phase space information into real stuff. So for example, you just have a lot of computers and you have them all, train them to do the rules of chess and just have them start playing chess, and you record every game. After a while, the amount of information required to describe every game ever played by these computers vastly exceeds the amount of information required to program the computers in the first place. And it's the contingent history of this computer choosing this chess move, and then this move chosen, and this move chosen, and this move chosen, which generates that real information. Or, starting from a clonal population of bacteria, microevolution increases the genetic diversity. So every real mutation happening in this population increases the amount of genetic information in the real population. Now, the next several examples here, I've indented them because they're all examples of this third one, contingent history information, contingent history of a system. It played out in different scenarios. So, next, the information required to fully describe an environment. So, starting from a simple uniform environment requiring very little information to specify, contingent historical events can produce a highly varied environment. A few years ago, I wrote a screensaver program. It started with a blank screen, and then there's just rules that say numbers 1 through 8, think of them as atoms, pop on with various probabilities, move with various probabilities, pop off with various probabilities. If they happen to move and touch each other, they'll bind together to form a molecule, and then that molecule moves with probabilities, and then the bonds can break, and they can rotate. And you watch it, and over time you see the screen fills up, and over time you see not just atoms, but here's a molecule of 2 atoms, and a molecule of 3 atoms, and a molecule of 5 atoms, and the environment gets very complex. It starts simple, and these rules just go on over time, and eventually you reach an environment that requires lots of information to describe everything that's going on because of all these contingent historical events. Of course, my favorite example is you start from the Big Bang, and shortly after the Big Bang, you got a pretty uniform environment of particles and photons, and then move that forward to 4.6 billion years ago, and look at the vast variety of things that are now in it. All the atoms in the periodic table, stars, galaxies, black holes, nebulas, gas giant planets, asteroids, even planets with dry land and oceans and atmospheres, and collections of small organic molecules. A very highly variable environment produced and requiring a lot of information to describe. All right, now we have a very complicated environment which requires a lot of information to describe. So now, how do we then produce more complicated things in that environment? So, once an environment is highly varied, like, say, the early prebiotic Earth, even if objects within it are fairly simple, deterministic and probabilistic laws, these contingent historical events, can sometimes, under some conditions, self-assemble new, more complex objects with novel properties. Particles combining to form atoms, combine molecules is one you're familiar with. I want to go back to this example. There's one molecule, this ring molecule, numbers 1 through 8, has a unique property in this program. Unlike any other molecule, it is stable. The bonds will not break. Unlike any other molecule, it moves exactly 1 notch per screen cycle. Now, there's no special rules which say once you have that molecule, you obey these special rules of being stable and rotating. No, those you would never see it in the math unless you spent a few hours looking for where I buried it, because these are emergent properties. The stability and the clock-like rotation of that molecule are emergent properties of the same math that governs every other molecule that is not stable and does not rotate exactly. but it forms, it self-assembles over time. So here you have a situation where within this complicated environment, if you wait long enough, something self-assembles that is more complex than anything seen before and has new properties that has never been seen before. So that's a computer example. This morning we saw this wonderful example. If you're looking for where to find the movie of this self-assembling capsid, there's the link. I didn't know this was going to be shown. So here's the really big question. In an environment, can you not just self-assemble complex things with novel properties, but can you actually self-assemble a self-replicator? That's the big abiogenesis question. And I'm going to point to a computer model, which I found very interesting. This is a computer model of the evolution of an autocatalytic set of chemicals. So they weren't modeling real chemicals. They were modeling theoretical chemicals, which were specified by, well, this reacts with all the other chemicals in this way, or doesn't react, or it upregulates or downregulates these reactions. And then let them react for a while, wash out the chemicals of which there's the least remaining amount, introduce one new random chemical, start it all over again, and every single time they run it over time, they eventually evolve an autocatalytic set of chemicals which combine to form these autocatalytic cycles that just take over, which is one path, some people say, to the origin of life. All right, now, if we can get a self-replicator that way, there's other kinds of information transformation that happen. Feedback loops, and this was discussed in some of the earlier talks, feedback loops between a varied environment and an object such as a self-replicator using variation and selection can greatly increase the information content of the object. We saw the biological examples. I would also point out that neural networks that can learn are a good example of it. Your brain is a good example of it. Cog, the robot, who learns about his environment by interacting with it, who is a computer model of a neural network, is a good example of that. Maze navigating programs that use genetic algorithms to learn how to navigate a maze can eventually build up instruction strings for navigating a maze that are vastly longer than the original program designed to initiate that that maze navigation. So the information content of the maze navigating program, by feedback with the environment and these selection mechanisms, can greatly grow. And then living organisms evolving and adapting to new environments. Final step I want to talk about is the interdependent complexity of a portion of the genome. So this is getting at more this interlocking complexity question. Evolving interlocking complexity, there's more than two ways it can happen, but two of the best ways are you have novel combinations, which then sometimes are positively selected, or you actually have the same stuff you always had before in your genome or in your population, but new selection pressures come in which happen on existing systems, and that increases the interlocking complexity of the system. Adaptive radiation to a new environment is a classic biological example. The mammalian middle ear is a classic example. I study ion channels, and I can tell you about some specific examples. There are what are called homogeneous ion channels, where one gene makes one protein, and 5 or 6 copies of that protein make a functional ion channel. But there are other ion channels which require 3 or 4 genes making 3 or 4 different proteins, all of which have to be in place for the ion channel to work. So that's an example of interlocking complexity. But we have really good evidence that they evolved via gene duplication and mutation from homogeneous ion channels. And then there's a computer model I've got students working on not today because it's Saturday, but all this summer and last. They were working on this program called Picariotes. It's a digital organism. It's a digital model of an organism that gathers chemicals from its environment, has a genome with a string of codons. It makes proteins from its gathered chemicals. The proteins sometimes form into complexes. Most proteins and complexes are non-functional. A few of them are functional. And after a certain number of genome reading steps, an organism's fitness is calculated based on how many chemicals it's gathered, and its fitness determines its reproductive probability. And there's various types of mutations, point mutations, deletions, copying, and so forth. And what we find when we run this under the certain set of circumstances, not all sets of circumstances, but under some, the genome length increases with time and with generation and the fitness. So the horizontal axis is the generation number, how many generations it's run. The top graph, the y-axis, is the fitness of the organisms, which is based on how many chemicals they've gathered. And the bottom graph is the average genome length, which, as you can see, is going up. So what about complexity? Well, we define complexity of an organism to start at 0, and then when it's starting to use proteins to gather chemicals, that's 1, and 2 protein complexes is a complexity of 2, and 3 protein complexes is a complexity of 3, and irreducible complexity has to do with non-functional subunits. So if you have a complex with 4 proteins, of which 1 is functional on its own, and the other 3 have absolutely no function, unless they're part of the complex, that would have a complexity of 4 and an irreducible complexity of 3. And what we see is both complexity and irreducible complexity evolve in a Darwinian fashion in our digital organisms. All right. Let's see. How much time do I have left? All right. So, we talked a bit about, the last speaker brought up these probability arguments again, and I'm very glad because I think it's useful to think about probability arguments versus information arguments on the origin of life. Sometimes they're framed in terms of probability, sometimes framed in terms of information. So let's look at the chess example. How does information happen with the chess? Well, the information required to specify the rules and initial conditions of chess is fairly modest. The combinatoric information is vast, the number of possible games, and the contingent history information can become vast by playing lots and lots of games of chess. Now, what about probability in chess? Well, here's one way to think about it. If you start from the standard opening set of chess, and think of this as the opening setup of pieces of chess is sort of like the prebiotic Earth, okay? If you start with the standard opening set of chess, there are certain positions of the pieces which are just plain impossible by the rules of chess. If you ever see the white king in the middle of the board completely surrounded by 8 black pawns with the black king off in the corner, and somebody told you that that happened by the standard rules of chess, you would know they were lying. Now, there's a certain number of positions which are very probable. You know, any arrangement of pieces that's 5 or 6 moves from the opening position is very probable. And if somebody says to you that computers played a game and this is where the chess pieces wound up, you'd say, well, yeah, easy. I can easily believe that. Now, most arrangements of pieces on the board are very improbable. In other words, if you started a gazillion computers playing the game of chess, it's very unlikely that any of them would happen to hit that one. But most of them are not particularly interesting. So if you see one of these arrangements of chess pieces and somebody says, you know, computers did this in a game, you would say, I don't see any reason to doubt that. It may be one of those vast number of improbable situations, but it doesn't look that interesting. But there are certain arrangements which would make you suspicious. For example, if you saw a white rook in the middle of the board, completely surrounded by black pawns, with both kings off in the corners, you saw that, and it's possible by the rules of chess, but you wouldn't believe it happened by the rules of chess. You would say somebody did that by hand. All right. Now, probability-based arguments against abiogenesis and evolution of complexity say, starting from the prebiotic Earth, it's impossible or very improbable to generate life. And I could imagine such arguments being convincing if future scientific arguments turned out certain ways, although I suspect right now that those future scientific experiments will turn out other ways and find that abiogenesis is indeed pretty probable. But let's look at the information. Information-based arguments against abiogenesis. I've read a lot of them. None of them convince me. And I'm skeptical that other ones will convince me because, as I said at the beginning, there are many kinds of information. Natural processes can create vast amounts of it, some kinds of information. They can convert some kinds of information into other types, and we can understand and at least partially model every step of the way. And I'm going to give you sort of a summary of them. Starting from simple objects, combinatorics creates a vast space of possibilities. Now, the symbols here This symbol here refers to a theoretical understanding of how this can happen, and we have that. This refers to computer models of such processes, and we have them. This refers to man-made objects which can do this, and we have them. This refers to natural physical systems which do this, and we have them. And this refers to natural biological systems which do this, and we have them. I haven't shown you examples of every one of them, but I could if you want to ask me about it later. Next step. When real systems navigate these combinatoric pathways via rules, which are partly deterministic and partly probabilistic, it generates real contingent history information. And we have examples in all 5 of those categories. Starting from a simple uniform environment, requiring little information to describe, natural processes produce a highly varied environment. There are examples in all 5 categories. Now, when it comes to self-assembly of complex objects with novel properties, I'm hedging a bit. I reduced the size of this theoretical understanding because our understanding is less. And I eliminated the biological one because we don't really start with a simple biological system, and we start with pretty complicated biological systems, which get more complex, but we don't have sort of self-assembly of complex out of really simple. And then the big question, can we self-assemble autocatalytic cycles and self-replicators? We have computer models of some of those. I put this symbol here to remind us that real crystal growth is kind of a minor example of this sort of thing happening. It is an autocatalytic cycle. It is a bit of a self-replicator. But the real question is, in the next few decades, will we be able to put a physical system with an arrow leading to a biological system in this category? I think we will. We will see. Now, once we have a self-replicator, feedback loops between a variable environment and that self-replicator can greatly increase the information content. We've got examples of those. And then once you have this happening, the interlocking complexity of that self-replicator can grow by various mechanisms. And here again, we have biological examples. I don't know of a good real physical example of it. In fact, I don't know of a good man-made example of this. But we do have good computer models of this. So, I sort of wrote a conclusion here. All the information needed for abiogenesis is in the combinatoric phase space of possible molecular combinations, okay? And Walter Bradley asked that question. Is it the case that those pathways are there such that it's very probable or very improbable that in prebiotic Earth we would find them? Contingent historical events, one molecule bumping into another in the early Earth and either reacting or not reacting, that converts all that potential information in the combinatoric phase space of molecules into real information about what was happening on Earth, describing real molecules and real systems. So information is not the barrier to first life. So the only remaining question in my mind is, what's the probability of it happening? So of all these steps, the reason I think that we probably will find ultimately good scientific explanation of abiogenesis is you look at all these steps from start to beginning, and it looks like a grand design to me. God has created physical systems and biological systems with all these kinds of information being created and transformed. And we humans have sort of followed after God, developing theoretical understanding and computer models and in some case real physical systems that do this. And it looks like a really cool pattern to me. So that's where I see the design coming in. One of the places I see the design coming in. So now I'm ready to take questions.
Thank you. Very timely. We've got 3 or 4 minutes here. Oh, I enjoyed your presentation. What's your view of work with Stuart Kaufman and Santa Fe Institute did for many years? Are you familiar with those? Because they were early people trying to develop computer models that did emergent things and so forth. And I think at the end of the day, I'm not sure if they're still doing that today or not, but they were often criticized because it was called factless science. It didn't. People said, yeah, you can get a computer to do anything if you give it the right set of rules, but it doesn't necessarily tell us much about what happens in real natural systems.
Right. So that autocatalytic chemical thing came out of work being done at that institute. The institute's still doing it. It is, in fact, I think they've reached a point where they said, our current models, given our current understanding of chemistry, can't help us do a lot more on abiogenesis. They're doing a lot more on agent-based modeling in the social sciences. They still are dabbling a bit in abiogenesis, but they've shifted to where they think their complexity theory can have a more immediate applications, waiting for more knowledge of RNA chemistry to sort of catch up with the and then maybe dive back in, is I think their plan.
Okay. Start yelling if you feel particularly low.
Both the previous speakers mentioned gravity as a metaphor and it's sort of the idea of an attractor. And I wondered if you have seen any ways in which, when you're talking about information-based arguments, do you see attractors playing any role?
Yes, but it depends on which of those 9 different kinds of information you're talking about. You know, in a computer's playing chess, the attractors are which tend to be the winning moves over the losing moves. In molecular self-assembly, it's these energy landscapes that we talked about. So, yes, in a lot of these examples, there are attractors, but it's probably different in every example. And for each of these 7 or 9 kinds of information, if you look at different theoretical or different physical or different biological, again, it's different. So there are some unifying themes which complexity theorists get very interested in trying to find what are the unifying themes. But there's always, you know, really fascinating differences in the details, depending on which kind of information you're talking about.
So on your one of your graphs, for your pipe karyotes, you had a graph showing complexity evolving and irreducible complexity evolving. What do you mean by what does that green graph, the irreducible complexity? How do you metrify?
So we actually worry about this. This is our first attempt to quantify the complexity, and we came up with a very simple metric. All our digital organisms start out by gathering chemicals, not using any proteins they make. And the first proteins that they ever learn to make don't actually help them gather chemicals. But eventually, some of them hit on a protein which helps them gather chemicals. And when that kind of takes over in the population and every organism is using proteins to gather each of the chemicals, we call it complexity 1. And when they start using complexes of 2 proteins bound together to gather the chemicals, because that lets them do it even faster, that's complexity 2. And eventually what happens is, after 2,000 generations with this set of initial parameters, all the organisms have come from a lineage where they've evolved a system where they now have complexes of 5 proteins or 6 proteins that they're using to gather chemicals. And if you have, as I said before, if you have a complex of size 4 proteins, that's a complexity of 4. If it just so happens that one of those proteins has its own function all by itself, it's functional. It helps gather chemicals. And the other 3 don't. They do not have, they're just drag on the system all by themselves until they combine into this complex. That would be a system with an irreducible complexity of 3 and a complexity of 4. I'm sure we can eventually think of better metrics of irreducible complexity, but that's the one we came up with so far.